let's do this following example. Let's say we want to compare two different methods of reading instruction to 11-year-olds. And the thing we want to measure is a score out of 100 on a test, on some sort of reading test after they have the instruction. So the two instruction methods are A and, I didn't write it here, but method B is the other method. And so for method A, there were 10 11-year-olds that they sampled randomly. The mean score was 76.4 with a standard deviation of 5.8348. For method B, they sampled 12 11-year-olds. Those 11-year-olds had a mean score on the test of 72.3 and a standard deviation of 6.3437. It's also assumed that the variances in each group are equal. Remember, variances is just the standard deviation squared, so if you want, you can think of this being standard deviations in each group are equal. And we want to know, at a significant level of 0.05, is there a difference in mean reading scores between the groups? So we want to do a hypothesis test on this data. So let's set up our null and alternative hypothesis first. So it's not quite said here, but when we're in this situation, when we want evidence that there is a difference, and evidence that something's happens, we have to assume that it doesn't happen first. So our null hypothesis is going to be that there's no difference in reading scores. That's what we're going to assume. That if we subtract the means of A and B, we get 0. And that's because we need evidence to show that there is a difference, so we're going to assume there's no difference until we have evidence otherwise. And the alternative hypothesis is going to be the opposite of that. We want that there is a difference. And it doesn't say if one is bigger than the other. We're not assuming anything like that, just that there is a difference, which means that the difference between the two means is not 0. There's no direction given about this difference, just saying that there is some sort of difference, so the mean isn't equal to 0. It's less than 0 or greater than 0. So now that we have our null and alternative hypotheses set up, we can decide what sampling distribution applies to this data. Also, I didn't say this, so I'm going to tell you right now. It's assumed that variances in each group are equal, and reading scores are normally distributed. So I'll tell you that as well. We're assuming that reading scores are normally distributed. Okay, so it's a good time maybe to pause the video and go to your flow chart talking about comparing two samples and decide what sampling distribution applies and calculating the standard error. And we'll do that on the next slide. Using our flowchart, we should see that we're going to get a t-distribution that has 10 plus 12 minus 2, so that's 20 degrees of freedom. We are dealing with a t-distribution where the variances are assumed equal. So the standard error is given by this formula here. And if you calculate that, you should get roughly 2.62. As a check, here is the pooled standard deviation, or squared, or the pooled variance here. So you can check if you're doing your calculation correct. So we're set to go. Let's draw, and let me write down as well that our level of significance was 0.05. So let's draw our sampling distribution. Remember, we're assuming that the null hypothesis is true, that there's a difference of 0. Now, we want an error of 0.05, but here we don't have a direction. So we're going to split that error up into two pieces, where this is a two-tailed test. So because we don't have a direction, we're going to put half the error on either side. So this is 2.5%, and so is this, for a total of an alpha of 5%. And this is a two-tailed. And you know it's two-tailed if you see your alternative hypothesis having a not equal to value there, some number. Let's call that number, I guess, capital N for number, whatever. But this is kind of the key there. If you see this not equal to, you know it's a two-tailed test. Okay, so we're almost ready. We just need to determine our rejection region first. So we're looking for, in our table, we're looking for t of 0.025 when there are 20 degrees of freedom. And if you look in your table, you'll find that that is 2.086. And over on this side, we're going to have negative 2.086. So anything that's more extreme than 2.086 standard errors from the mean, we're going to say is too extreme for us to believe that the difference is actually 0. Okay, so now we compute our test statistic, our t star. So remember, our t star is going to be our differences. So I'll just write it down here. So xa minus xb minus the population means, we're assuming mu a minus mu b over our standard error. And we know all of these things. So this is 76.4 minus 72.33 minus, well, we're assuming that this difference, that's the null hypothesis, we're assuming that that is 0. So that is by the null hypothesis. And we're going to divide that difference by 2.62. And if we do that, we get that our t star is 1.55. So where is 1.55 in our diagram here? Well, 1.55 is there. That's 1.55 standard errors from the mean. There's our t star. So it's not in the rejection region. It's not extreme enough for us to say that the mean isn't 0. So our test statistic does not lie in the rejection region. So we do not reject the null hypothesis. So there is no, or not strong enough, evidence of a difference in mean reading scores. I'm running out of space here, so I'll just draw it. I'll just write it in shorthand here. And there we go. There is another hypothesis test. Again, once we decide what sampling distribution to use and what a rejection region is, then it's just a matter of determining if our sample is too extreme for us. In this case, it wasn't. It wasn't in our rejection region. So we say that's not extreme enough for us to reject the null hypothesis, so we don't reject it.